In this lecture video, we're going to look at non-parametric analysis of data from a randomized complete block, or RCB, designed experiment. Now, the Kruskal-Wallace test is a non-parametric method used to analyze data from what is called a completely randomized design, or a CRD. A CRD is appropriate when the experimental units used in a design experiment are homogeneous, and treatments are assigned to the experimental units completely at random. However, when the experimental units are not all homogeneous, then the CRD will not be optimal. In some situations, experimental units that are not all homogeneous can be partitioned into groups that are homogeneous. Such grouping is called blocking, and the groups are called blocks. Now, when blocking is used, it must be accounted for in the analysis in order to be able to make valid inferences. In particular, it would not be appropriate to use the Kruskal-Wallace test that we've seen before, and again, which is designed for CRD or completely randomized design data, on data from an experiment that has an RCB or randomized complete block design. An analysis that can be used to analyze data from an experiment with an RCB design is known as Friedman's test. Now, there are other names for this test, or tests that are very, very similar to this. For example, one is called Cochran's Q test. Okay, these are all essentially the same type of test. The bottom line is that they allow us to perform a comparison of populations within the context of a designed experiment that has a randomized complete block design. Now, let's denote the number of treatments used in an RCB experiment by lowercase t, and denote the number of blocks by lowercase b. Then the test statistic that we'll use for Friedman's test is given on the next slide. So on this slide, we actually have the hypotheses that we're going to be testing. The test statistics on the next slide. But on this slide, this is the hypotheses that we'll be testing. And you'll see that it's the same set of hypotheses that we were testing in the Kruskal-Wallace test. Now, in this setup, we're using just a little bit different notation. When we talked about the Kruskal-Wallace test, we denoted the number of populations by K. In this context, we're going to denote the number of populations by lowercase t. And so t is the number of treatments, or the number of populations under consideration in a given situation. And then again, the number of blocks is denoted by lowercase b. Now, we're going to perform this test at a significance level of alpha. Okay, so here's the slide with the test statistic. So how do we go about calculating the value of the test statistic? Well, the first step is to rank the treatment responses within each block separately. So we're not going to combine the observations into one common sample. We're going to keep the observations in their separate blocks, and within each block, we're going to rank the observations. And we handle ties in the way that we usually do. And then what we're going to do is we're going to denote, for purposes of calculation and notation, we will denote the rank of the ith treatment response in the jth block by cap r sub ij. So we've got, again, t treatments, I going from 1 to t, and we've got b blocks, j going from 1 to b, and so r sub ij is the rank of the ith treatment response within the jth block. Okay, once we've done that, then we obtain the sum of the ranks for each treatment. So what we have to do is, for a given treatment, for example, treatment 1, we have to find the rank of that treatment within each of the blocks, and then add those ranks up. And we're going to denote the sum of those by cap r sub I. And then using the r sub ij's and the r sub i's, we're going to calculate two additional values. So a is equal to the sum of all of the r sub ij squareds. So we're going to take these r sub ij's and square each of them, and then add those squared values up. And then we're going to take the r sub i's and square those, add those up, and divide that sum by lowercase b, the number of blocks, and we're going to call that capital B. So once we have those values, we know lowercase b, the number of blocks, we know lowercase t, the number of treatments. Then we're going to calculate the test statistic, which we're going to call t star, using this formula here. And then the rejection criterion. Some references will have you compare t star to a critical point from the chi-square distribution. But other references recommend using the F distribution, and they say that this gives us a better test. So my guess is that it's more powerful, and remember, power is a good thing. Power is the probability of rejecting the null hypothesis when it's false, and therefore should be rejected, and we want that probability to be as high as possible in a given situation, so we want as much power as possible. So we're going to use this f-test. There are t-1 numerator degrees of freedom, and the denominator degrees of freedom is given by t-1 times the quantity b-1. All right, so that is the procedure. And so now let's look at an example of this. All right, so again, what this is analogous to doing is doing an ANOVA when you have a randomized complete block design. And to contrast that with what we did with the Kruskal-Wallace test, the Kruskal-Wallace test was analogous to an ANOVA when you have a completely randomized design. So again, what we're doing here is comparing two or more populations, just like we did in the Kruskal-Wallace test, but in this particular context, the data come from an experiment that has a randomized complete block design. So in this example, we're going to use Friedman's test to analyze data from an experiment laid out in randomized complete blocks that is designed to compare the effectiveness of 5 weed killers. All right, so this is a very interesting and very realistic type of example. So an experiment was conducted to compare the effectiveness of 5 weed killers. 3 plots of ground were available for the study. So for example, maybe they were on 3 different farms, or maybe on an agricultural research farm, but in different areas of that farm. We've got 3 plots of ground that are available for the study. And if the plots of ground are spatially distant from each other, then it's very likely that they will be different from each other, so that the 3 plots will be heterogeneous with respect to each other, but the ground within the plots would tend to be more homogeneous. So each plot was divided into 5 strips. Strips within plots were homogeneous, whereas strips between plots were heterogeneous. And so therefore, the plots were treated as blocks, and a randomized complete block design was used for the experiment. Within each block, each weed killer was randomly assigned to 1 strip and then applied to the weeds in that strip. And at the end of the study, the percentage of weeds killed was recorded. The response variable that's being measured here, that's being recorded, is the percentage of the weeds killed in a particular strip. So let's keep that in mind for a second here, because, and this is why this is important to consider, when a response variable is a percentage or a proportion, and there are many situations in which that's the case, we need to understand that that kind of data is very often non-normal, and also the variability varies because the variability depends on the actual proportion or percentage. I mean, if you think about, for example, a binomial distribution, then as the success probability changes, so does the variance. And remember, one of the assumptions about the standard analysis of variance is that the variability is the same from one population to another. Well, if the response variable is a proportion or a percentage like this, then that assumption is more than likely violated. And so because of that, in many situations where the response variable is a percentage or a proportion, analysis of variance is not done. In some cases, they may transform the response from a proportion into another quantity in an attempt to mitigate differences in the variances. But another approach is to use a nonparametric approach. So this is what we're going to do here. We're going to use Friedman's test rather than the usual ANOVA. So the question to be answered in this situation is whether there is sufficient evidence at the 0.05 level of significance to conclude that the weed killers differ in their effectiveness. So we've got these 5 weed killers represented by the 5 populations. The null hypothesis is that the 5 weed killers are the same in terms of their effectiveness in killing weeds. And the alternative is that they are not the same, that there are differences, that at least one of the weed killers is different from the others. So that is the hypothesis that we're going to test. Okay, so on this slide, we've got the data along with the ranks in parentheses. And so remember, the responses here are the percentages of the weeds killed. And notice that not only do we have the weed killers represented by the rows, but the columns, at least these 3 columns, correspond to the 3 blocks. So within block 1, weed killer 1, the strip to which weed killer 1 was applied, in that strip, 16% of the weeds were killed. 1% of the weeds were killed in the strip to which weed killer 2 was applied, and so forth. And you see these. Similarly for the other columns here. And then notice that in parentheses we've got the ranks. Now, we really don't even need a spreadsheet to calculate these ranks. We could rank these by eye because there's so few of them, and we can even easily handle ties. So 1 is the smallest value here, so that obviously gets rank 1. The next larger value is 4. Well, there are 2 of those, and so these would get ranks 2.5 and 2.5. And then the same thing with these 2 cells for the responses that were each 16. So it's very easy to rank responses within each block, and so we're just going to do that by eye. We're not even going to have to run a program or build a spreadsheet or anything. Once we have done that, then we're going to, let me back up a second. The values in parentheses are the R sub ij's. Then what we're going to do is we're going to add up the R sub ij's within each row, and that gives us R sub I for the treatment corresponding to that row. So for weed killer 1, R1 is going to be 4.5 plus 5 plus 4.5, and that gives us 14. The same for the rest of the rows. Then I've added another column here to help out with calculations. This is R sub I squared, so I'm just squaring the values in this column, and so we get those values. Okay, so then let's look at calculating the test statistics. So capital A is the sum of all the squared values of the R sub ij's. And so we square the values in these parentheses and we add those up, and when we do that we get 163.5. Capital B is 1 over 3, 1 over B times the sum of the squared R sub I values. Well, I'm just going to add up the values in this column and then divide that sum by 3, and I get 155.167. Then once I have those values, I can calculate T star, the test statistic, using the formula given, and I end up getting 4.84. So that's the value of the test statistic, and now we need to evaluate that by comparing it to the appropriate critical point. Remember, that critical point is going to come from the F distribution. The numerator degrees of freedom is 1 less than the number of treatments, so 4. And then the denominator degrees of freedom are t minus 1 times the quantity b minus 1. So 5 minus 1 times the quantity 3 minus 1. 4 times 2 are 8. So we've got 4 numerator degrees of freedom and 8 denominator degrees of freedom. So therefore, when we look up this value in the 0.05 F table, we get 3.84. The rejection criterion then is to reject the null hypothesis if our test statistic T star exceeds 3.84. And since 4.84 is, in fact, greater than 3.84, the rejection criterion has been met, and so therefore we would reject the null hypothesis at the 0.05 level of significance and conclude that differences do in fact exist among the 5 populations. And so translating this back into the language of the problem, we can say that there is sufficient evidence at the 0.05 level of significance to conclude that differences exist in the effectiveness of the 5 weed killers. Okay, so that is the end of this example. So we've answered the question. We were assuming that the weed killers are all equivalent, they're all the same in terms of their effectiveness. We've rejected that assumption, we've rejected that hypothesis at the 0.05 level of significance, and we're concluding that the populations are not all the same. And in the context of the problem, we would say that the weed killers are not equal in terms of their effectiveness. At least one of the weed killers is different than the rest in terms of its efficacy. And so a very natural question would be, where are the differences? Which weed killers are different from the others? And so to answer that question, we're going to do the same kind of thing that we looked at when we were looking at the Kruskal-Wallace test. We're going to look at follow-up analyses to a significant Friedman test. So when the null hypothesis of the Friedman test is rejected, and therefore it is concluded that differences do exist among the populations, or equivalently among the treatment means, the natural follow-up question to answer is, where are the differences? Now, this is the same type of follow-up that we used for a significant Kruskal-Wallace test, and also that we would use for a significant ANOVA if we were operating in a parametric setting. Now, in this section, we're going to see how to follow up a significant Friedman test in the context of an RCB design and answer this natural and very important question. So as a reminder, the null hypothesis tested by the Friedman test is the following. We're testing the null hypothesis that all T populations, or equivalently all T treatments, are the same, against the alternative that differences exist among the populations, and in particular with respect to location. As before, we will investigate where the differences are by performing pairwise comparisons. A null hypothesis for such a comparison would be that population I is equal to population J against the alternative that population I is not equal to population J. Now there are T populations, and so there are choose 2 such pairwise comparisons. All right, so let's look at this procedure for making pairwise comparisons. So again, we've got the hypotheses that we'll be testing in each case for each pairwise comparison. And the test statistic is given by this expression here at the bottom of the slide. We're going to call this t-calc because, you guessed it, when we look up the critical point, that critical point is going to come from a t-table. All right? Now notice that the denominator, there's no quantity here that is subscripted. And so what that means is that for all pairwise comparisons, the denominator is going to be the same. So we only have to calculate that once, which is really, really nice. The only thing we're going to have to calculate specifically for each different comparison is the numerator. Now the rejection criteria for the test, we're going to reject the null hypothesis if t-calc is either really small or if it's really big. In order to look up a value from the t-table, we have to know how many degrees of freedom we're dealing with. And for this pairwise comparison, the number of degrees of freedom is equal to t minus 1 times b minus 1. Now remember, that was the denominator degrees of freedom in the f-test for the overall freedom test. So that is the number of degrees of freedom for this pairwise comparison that utilizes the t-distribution as the reference distribution. And then the p-value for the test can be calculated as well, or at least approximated if we only have the table. Because this is a two-sided test, the p-value is 2 times the probability that a t random variable with t minus 1 times b minus 1 degrees of freedom is at least as big as the absolute value of our test statistic. So again, the formula for this p-value should look very, very familiar to you at this time because, for example, that's the same format as the p-value for, let's say, the Kruskal-Wallace test, and also for two-sided t-tests in general. Okay, so let's continue with our example. We're analyzing this data from this experiment, this designed experiment. This experiment laid out in randomized complete blocks, the purpose of which is to compare the effectiveness of 5 weed killers. So in the previous example, 4.1, we used Friedman's test to compare the effectiveness of the 5 weed killers, and we concluded at the 0.05 level of significance that differences do in fact exist among the 5 weed killers in terms of their effectiveness at killing weeds. And so the natural and immediate follow-up question is, which weed killers differ from each other? And so we're going to answer that question by performing pairwise comparisons. Now, it's always good to know how many comparisons you're going to have to make in order to do something like this. And because there are 5 populations or 5 weed killers that we're comparing pairwise, there are 5 choose 2 or 10 pairwise comparisons that we're going to have to make in order to fully answer this question. So again, I've got the data from the original experiment. And now there are some quantities that are common to all of the pairwise comparisons, all 10 pairwise comparisons that we're going to have to make. And so we'll just state those here so we don't have to replicate them for each test. So all pairwise comparisons that we're going to do will be done at a 0.05 level of significance. The number of overall populations, or the number of overall weed killers in this instance, is 5. So let's remember that. T is equal to 5. The number of blocks in the experiment was 3. The degrees of freedom associated with each of these pairwise comparisons is 8. And the critical point, or let me say the t value, because we've got lower and upper critical points. So the upper 2.5 percentage point of the t-distribution with 8 degrees of freedom is 2.306. And you can look that up in the t-table. And so from that we get our rejection criteria. We're going to reject the null hypothesis if t-calc is either less than the lower critical point of negative 2.306, or if it's greater than positive 2.306. Now remember, we said that the denominator of the test statistic is the same for all pairwise comparisons because none of these quantities have a subscript on them. And so we can calculate the common value here. It's equal to 2.5. Okay, so now let's start looking at our comparisons. So we want to compare first weed killers 1 and 2. And so these are the hypotheses that we're testing. And notice that I've expressed them in terms of weed killer, so weed killer 1 and weed killer 2 being the same, being the null hypothesis, against the alternative hypothesis that the 2 weed killers are not the same. And we know that what this really means is that they're not the same in terms of their effectiveness. So the value of the test statistic, in this case, is 2.8. I've already calculated the denominator, and all we have to do now is take the difference between the two R values here. We get 2.8. And since 2.8 is greater than the upper critical point of 2.306, we reject the null hypothesis. All right, so let's kind of keep that in the back of our mind. All right, then we're going to compare weed killers 1 and 3. So you can see here the test statistic, 0.8. Since 0.8 is not less than negative 2.306 and it's not greater than positive 2.306, the rejection criteria have not been met, and so we're going to fail to reject the null hypothesis in this case. So there's insufficient evidence at the 0.05 level of significance to conclude that weed killers 1 and 3 are different in terms of their effectiveness in killing weeds. Okay, comparing weed killers 1 and 4. All right, so we've got the hypotheses up here. The value of the test statistic is 2.6, positive 2.6, and so because that exceeds the upper critical point of 2.306, the rejection criteria have been met, so we're going to reject the null hypothesis. So there is sufficient evidence at the 0.05 level of significance to conclude that weed killers 1 and 4 are in fact different in terms of their effectiveness, and we would conclude based on some of the ranks, the R values, that weed killer 1 is more effective than weed killer 4. All right, and then finally, weed killers 1 and 5. All right, so in this case, the test statistic is 3.8. And again, that is bigger than 2.306, and so we're going to reject the null hypothesis. So there is sufficient evidence at the 0.05 level of significance to conclude that weed killers 1 and 5 are different. And in fact, we can discern here, we can deduce that weed killer 1 is better than weed killer 5. Next, we're going to compare weed killers 2 and 3. And so in this case, the test statistic t-calc is negative. Since a negative 2 is not less than negative 2.306, and also it's not greater than positive 2.306, the rejection criteria have not been met, and so we fail to reject the null hypothesis. So there is insufficient evidence at the 0.05 level of significance to conclude that weed killers 2 and 3 differ in their effectiveness of killing weeds. Next, we compare weed killers 2 and 4. And the test statistic there is negative 0.2. Again, that is not less than negative 2.306, and it's not greater than positive 2.306. And so we fail to reject the null hypothesis. Right? There is insufficient evidence at the 0.05 level of significance to conclude that weed killers 2 and 4 differ in terms of their effectiveness. And then finally, weed killers 2 and 5. So in this case, the value of the test statistic is 1. That is not less than negative 2.306, and it's also not greater than 2.306. And so again, we fail to reject the null hypothesis. So there is insufficient evidence at the 0.05 level of significance to conclude that weed killers 2 and 5 differ in terms of their effectiveness in killing weeds. Moving on to the next comparison, so comparing weed killers 3 and 4. So here the test statistic turns out to be 1.8, and again we're going to fail to reject the null hypothesis. All right, and then we compare weed killers 3 and 5. Okay, now in this case, the test statistic is positive 3, and because that is bigger than the upper critical point of 2.306, we're again going to reject the null hypothesis. So there is sufficient evidence at the 0.05 level of significance to conclude that weed killers 3 and 5 are different in terms of their effectiveness in killing weeds. And in this case, weed killer 3 is better than weed killer 5. All right, and then the 10th pairwise comparison. Like I said, there's a lot of work here. So the test statistic here is 1.2. And so since that is not less than negative 2.306, and also it's not greater than positive 2.306, the rejection criteria have not been met. And so we fail to reject the null hypothesis. So there is insufficient evidence at the 0.05 level of significance to conclude that weed killers 4 and 5 differ in terms of their effectiveness. Okay, so we've got 10 different results, right? The overall test, we've concluded that differences exist among the 5 weed killers, and then we did these 10 follow-up tests. Did you keep track of them? Which is different than which? And how would you present this information? How would you summarize that information in a nice, concise way? Well, one way to do it is to use the same kind of approach that you would use when doing ANOVA. So think back to your first methods class when you did analysis of variance. And if you did multiple comparisons, follow-up pairwise comparisons, following a significant ANOVA, then you may very well have looked at a diagram kind of like this. And so what we've done here, okay, so this is my summary of pairwise comparisons that's going to allow us to answer which weed killers are different from each other. So if you look at this, what I've done is I've ranked in descending order, according to the sum of the ranks, the weed killers. So weed killer 1, I had a sum of its ranks of 14. That's the largest, and then weed killer 3 was the second one in descending order, and then so forth. So in terms of this rank here, it's weed killer 1, and then 3, and then 4, 2, and 5. And so what I've done is connect weed killers with a line if in fact they are not significantly different, if we failed to reject the null hypothesis that they were the same. And so when we compared weed killers 1 and 3, we failed to reject that null hypothesis, and so they get connected with a line. But when I connected weed killers 1 and 4, they were different, so I do not extend that line. I do not connect 1 and 4 with that line. And the same thing with weed killers 1 and 2 and 1 and 5. Those were all significantly different. So in terms of what was not determined to be different from weed killer 1, it was weed killer 3. Now I'm going to move over to the right just a little bit. I'm going to compare things with weed killer 3. So which of the weed killers were not significantly different from weed killer 3? Well, it was 4 and 2. And so those get connected with a line. However, weed killer 5 was significantly different from weed killer 3. So I don't extend that line down here. And then finally, I'll go here with weed killer 4. Okay, what was not significantly different from weed killer 4? Well, 2 was not significantly different from weed killer 4, and neither was 5. So I'm going to connect those 3 weed killers with a line. And so what we can see here, that weed killers 1 and 3 are not different from each other. Weed killers 2, 4, and 3 are not different from each other. Weed killers 4, 2, and 5 are not significantly different from each other. Weed killer 1 is different from weed killers 4, 2, and 5. Weed killer 3 is different than weed killer 5. Those are the extent of the differences among the 5 treatments. Okay, so that is the end of this example, and it's the end of what we're going to look at in terms of non-parametric analyses of data from a randomized complete block design. And so anyway, I hope this is useful. I think this is going to be very applicable, especially for you folks who are in agriculture. For example, randomized complete block designs are used very much in agriculture. In addition, for you folks in engineering, doing research in engineering, randomized complete block designs are very often used in that situation as well. And they're used in other areas also. So I think that because this is such a very common design, that I think that you're going to find this technique very useful as an alternative to doing the standard analysis of variance when you feel that some of those assumptions that underlie analysis of variance are violated.